James Webb's hunt for distant galaxies keeps turning up surprises. Recently, astronomers' jaws hit the floor when our premier observatory aimed its massive mirror and sensitive spectrograph at an incredibly old galaxy dating to just 120 million years after the Big Bang. It is like someone had drained the lake, and the monster is sitting there at the bottom, and this galactic Nessie is not alone. So far, James Webb has turned up thousands of distant galaxies dating to the early universe, many more than astronomers had expected. Some of those galaxies are brighter, more massive, or more mature than astronomers would have thought. They are now scratching their heads trying to explain how the galaxies could have grown up so fast. Join us as we dig deep into how James Webb just unveiled early the universe is different than we thought. To start, it's helpful to recall what the James Webb Space Telescope was built for. On Earth, astronomers often build telescopes on mountaintops and in remote deserts for an unobstructed view of the sky, but the Earth's atmosphere still mars the view. Space is the ultimate mountaintop. As NASA explains, James Webb launched in December 2021 as the successor to the Hubble Space Telescope, and it improves on its predecessor in several ways. For instance, because of its huge golden mirrors and infrared cameras, it can make better observations of planets orbiting stars other than our Sun. But for this discussion, what matters is how it can observe farther back in time than the Hubble telescope. In astronomy, the farther away an object is in a telescope's mirror, the older it is because light needs time to traverse such large distances. Some of the light JWST captures is almost as old as the universe itself, dating back to 100 million to 250 million years after the Big Bang, the relatively infant days of our universe, which is believed to be 13.77 billion years old. That light is so far away, it has been traveling nearly the age of the universe to reach us. So when James Webb focuses its mirrors on a particular patch of sky, it can see through time. The farthest objects in the image are the oldest, those in the foreground are more current. The images that contain this rich history are called deep field observations, and while they appear in 2 dimensions to us, in them, scientists can see how the universe has evolved. Before James Webb, the Hubble Space Telescope gave humanity its deepest look into the evolution of space, and in the Hubble images, scientists saw a pattern. As they peered farther back in time, there were fewer and fewer galaxies, and they were smaller and smaller. This makes intuitive sense. Just like fossils in the oldest layers of the Earth's crust represent more primitive forms of life, the oldest galaxies in a deep field image ought to represent more primitive galaxies. They differ from modern galaxies because they had the shortest amount of time to assemble. They were like teenagers compared to the large adult galaxies of today. When James Webb went online, astronomers were eager to peer a bit more deeply into the past. They thought the pattern from the Hubble images would just continue, and we would maybe see a couple of more galaxies, but they would be very, very rare. However, that's not what James Webb found. When James Webb turned on, it was apparent that there was a lot more light back then and a lot more galaxies. Even though the galaxies appear to our eyes as smudgy blobs, scientists can study the quality of light coming from them and make inferences about their size and age. James Webb has found really mature, large, bright galaxies back even farther than we expected, and according to early analyses, many of these galaxies were apparently huge, full-fledged adults, not teens. To further the fossil metaphor, it would be like finding evidence of advanced life forms in layers of the Earth when life ought to have been just starting out. In more fun terms, it's like at the earliest times, the universe was having a party and we had no idea it was happening. Okay, you might be thinking, so what? We got big, bright, plentiful galaxies way back near the beginning of time. Unexpected perhaps, but it's not like it's violating the laws of physics, right? Well, the problem is time. It's kind of like if you were flipping through a family photo album and came to the realization that your grandmother grew to be an adult from an infant in just a couple of months. Such a finding might make you wonder if we're missing a big piece of understanding human development or if somehow the pace of human development worked differently in the past. If these galaxies contain the number of stars implied by these early observations, it should be nearly impossible for them to exist. So what explains these bright, large galaxies? We don't yet know, but the most extreme possibility is that scientists are missing a big piece in their understanding of cosmology. The best model we have for the evolution of the universe is the Big Bang. According to this model, the early universe was a place of extremes. It was inconceivably small and scorching, with all the energy and matter there would ever be crammed into a tiny space a billion times hotter than the center of the sun. In the first moments after the Big Bang, the universe cooled enough to allow fundamental particles such as quarks and electrons to spring into being. Quarks combined to form protons and neutrons, and not long after, the nuclei of hydrogen, helium, and lithium were formed. Energy zipped around the infant universe in the form of photons, but that early light ricocheted off free electrons, which weren't yet bound to any atom at every turn. Fast forward another 380,000 years, and the universe had cooled enough to allow the early nuclei to pull in electrons and form neutral atoms. This is called recombination, although it actually marks the first time these particles combined. This moment ushered in darkness, a period we now call the cosmic dark ages. Looking at an object either with our eyes or with a telescope requires photons of light to hit some sort of detector, whether it's your retina or a camera. But the cosmic dark ages were a time when the universe was enveloped by a fog of neutral hydrogen that trapped the light of the first stars and galaxies. The fog didn't lift until 1 billion years after the Big Bang, when the neutral hydrogen had been reionized and once again split apart. Because light couldn't escape its surroundings during the dark ages, it couldn't journey outward through the universe to hit our detectors here on Earth nearly 13 billion years later. As a result, trying to peer back at that time is like trying to see a light bulb through a thick dark haze. But interesting things were happening, even if we can't see them. Think of our own dark ages here on Earth, between about AD 500 and 1000. It may not seem like much happened in terms of scientific or cultural advancement, but stirring beneath the surface were forces that would set in motion the Renaissance. Similarly, the cosmic dark ages were a time of great transformation. According to Avi Loeb, an astronomer at the Harvard-Smithsonian Center for Astrophysics who was among the first to explore this time in the early universe, this period is special in the sense that it marks the transition between the universe being very simple and being very complex. Black holes, neutron stars, even life eventually here on Earth, the roots of it were planted at the Dark Ages. If we want to understand where we came from, that's where the story starts. Astronomers do know what the universe was like just before the Dark Ages began. That's because they have an actual image of what conditions were like at that time. When the first neutral atoms formed, the process released photons of light that set off across the universe, creating a cosmic snapshot of the exact conditions at the beginning of their journey. This cosmic microwave background radiation, also known as relic radiation, exists all around us today and tells astronomers that the universe was more or less uniform in density at that time, with only very small ripples in it. But those ripples are important. If you feed those perturbations into a computer simulation, you get objects like galaxies we see today. But the precise way in which that transition happened is still poorly understood. What astronomers do know with certainty, however, is why we can't see any light from objects shining during the Dark Ages. For starters, there wasn't much light before the first stars formed. Aside from hydrogen atoms, most of the universe was made up of dark matter, which doesn't emit light. What's more, a cosmic fog of neutral hydrogen atoms permeated the universe, scattering or absorbing many of the ultraviolet photons that the very first stars emitted. The time it would take for a photon to escape the hydrogen was longer than the age of the universe, so light can't reach us from that time, however long we wait for it to arrive. But the Dark Ages didn't last forever. Astronomers believe that if they look far enough out into space, which means far enough back in time, they should eventually see where reionization occurs. This will be the boundary between the old dark universe and the newer, transparent one. Key discoveries such as the expanding universe through Hubble's observations and the Big Bang Theory's predictive success have grounded our cosmic understanding in observable phenomena, revealing a universe that was once hotter, denser, and more uniform. Despite significant advances, the earliest moments and the fundamental cause of the universe's inception remain shrouded in mystery, perhaps forever. So as we try to push the reach of our theories to earlier times, we move up in energy from atomic and nuclear physics to particle physics. After all, the earlier you look at the universe, the hotter and denser it was, and so the particles that filled up space had higher energies. Thus, to dive deeply into the cosmic infancy, physicists must use concepts from high-energy physics. Going beyond experimental results with some confidence, we could push the clock back to times just a second after the Big Bang, but here, the cosmic picture becomes murkier. It may be that the best we can ever do is to ask what the universe looked like a billionth of a second after the Big Bang. Beyond that, we're probing regimes that may forever be hidden from view. In these extreme conditions, it's thought that even the known laws of physics might have broken down, giving way to unknown principles. Astronomers can still see the moments that ended the Dark Ages because the process of reionization allowed light to travel through space again. The birth of the first stars, galaxies, and black holes eventually generated the ultraviolet radiation that cleared out the cosmic fog and reionized the neutral hydrogen. So the end of the Dark Ages was effectively like the universe flipping on the lights. What's extraordinary about James Webb's findings is that the light seemed to have come on in full force. Early analyses of the latest James Webb observations hint that the first stars and galaxies formed faster and more furiously than previously thought. During the Dark Ages, there should have been fewer stars, smaller galaxies, and a slower cosmic evolution pace, yet here we are with James Webb showing a universe brimming with activity soon after the Big Bang. So these new observations challenge our understanding of the early universe's timeline and the formation processes of stars and galaxies. These findings will surely spur astronomers to revise models of early galaxy formation and star birth. The presence of large, mature galaxies just 120 million years post-Big Bang suggests that either the processes we think drive galaxy formation are more efficient than we believed or that there are new, unknown processes at play. One possibility is that these early galaxies experienced a period of rapid star formation, an accelerated phase that hasn't been fully accounted for in existing models. Another intriguing prospect is that dark matter, which is thought to make up most of the universe's mass and plays a crucial role in galaxy formation, might interact in ways not yet understood. There's also the consideration that our measurements and interpretations need refining, but whatever the case, these revelations from James Webb highlight the need for further exploration and study. To put it in perspective, imagine you're watching a documentary series about the history of life on Earth, expecting to see single-celled organisms evolve gradually into complex life forms. Instead, you suddenly come across a scene where fully developed, diverse species appear almost out of nowhere, challenging everything you thought you knew about evolutionary timelines. That's what these new discoveries feel like to astronomers. They don't just fill in gaps in our understanding, they rewrite entire chapters of the story. In summary, the James Webb Space Telescope is providing unprecedented insights into the universe's early days, revealing a more complex and dynamic cosmic infancy than previously thought. These findings challenge existing theories and open new avenues for research into the origins and evolution of galaxies. As we continue to analyze the data and refine our models, the early universe's true nature and the processes that shaped it will become clearer, offering a deeper understanding of the cosmos and our place within it. Radiation simply streamed freely amidst the sea of atoms. But why wasn't this radiation blocked by the now intervening neutral atoms that populate the abyss of empty space? The reason is wavelength. It only streams freely through the atoms due to the fact that the cosmic radiation was much lower in energy than neutral atoms, mostly hydrogen, are capable of absorbing at wavelengths too long for absorption to take place. If the radiation were higher in energy, atoms would not only absorb it, they would residential scatter it in all directions where it would be further absorbed by additional atoms. It's only because the radiation is so low in energy, it's primarily infrared light, that it can freely pass through the space that neutral atoms occupy. The light-blocking effects of neutral atoms are so good at visible and ultraviolet wavelengths, but so poor at inherently infrared wavelengths, that this plays out not only in the very early universe but in modern times as well. We see this even in our own galaxy. The stars and objects that persist in the Milky Way's galactic center cannot be seen in visible light. The dust and gas that are present block it, just as they efficiently block visible light all throughout the galactic plane. However, at longer wavelengths, infrared light goes clear through those neutral atoms. This explains why the cosmic microwave background doesn't get absorbed, but starlight does. Thankfully, the stars that form in the universe, particularly early on in cosmic history, can be massive and hot, where the most massive ones are much more luminous and hotter than even our Sun. Early stars can be tens, hundreds, or even thousands of times as massive as our own Sun, meaning they can reach surface temperatures of tens or even hundreds of thousands of degrees and brightnesses that are millions of times as luminous as our Sun. These behemoths are the biggest threat to the continued existence of any neutral atoms that happen to be spread throughout the universe. What determines whether atoms remain neutral and capable of absorbing visible light or whether they become ionized and transparent to the light that our eyes typically perceive? It's all about the energy of the radiation that strikes them. The key property of whether an atom becomes ionized by the nearby stars is that for stars above a certain temperature, they'll emit some fraction of their light in the ultraviolet portion of the spectrum, energetic enough to ionize a neutral atom. And remember, at all moments in cosmic history, even today, the most common atom in the universe by number is hydrogen. More than 90% of the atoms present are still simply hydrogen. For a hydrogen atom in its lowest energy state, it takes a photon of 13.6 electron volts or more to ionize it, which very few photons emitted from most stars possess. But that's because most stars have their energy peak in either the visible or infrared portion of the spectrum, with fewer high-energy photons above a certain ultraviolet threshold. However, the hotter and more massive your star is, the more ionizing photons they produce. Because these are the shortest-lived stars, it's only within a few million years of forming a new burst of stars that you get an excessive amount of ionizing photons, which coincides with large numbers of hydrogen atoms being ionized. If you were to imagine a scenario in which all atoms inhabiting the universe became ionized, the depths of star-free space would be clear for light to travel through, meaning we could see the distant universe without a problem. All the starlight that was emitted would freely propagate through space, and none of it would be extinguished unless and until it arrived at the proverbial eyes of an observer. But even so long as a small percentage of the atoms remain neutral, that emitted starlight could be effectively absorbed, making it extraordinarily challenging to detect anything from the era of the first stars and galaxies. It's true that a smaller percentage of neutral atoms means that starlight must travel through larger numbers of them to be fully absorbed, as the extinction of light in astronomy is cumulative. What we need to happen if we want the universe to become truly transparent to starlight is for enough star formation to occur that it floods the universe with a sufficient number of ultraviolet photons to ionize the neutral matter in the intergalactic medium so that starlight can travel unimpeded. This requires a large amount of star formation and requires it to occur quickly enough that the ionized protons and electrons don't find one another and recombine again. The very first stars in the universe make a small dent in the population of neutral atoms surrounding them, but the earliest of the star clusters are small and short-lived. The universe will remain largely neutral with them alone, especially once the most massive of those stars die and neutral atoms reform. The second generation of stars, formed in the aftermath of the first generation's death, fare little better. The big problem is that these newly formed stars form in clumps and clusters of perhaps a few million solar masses at most. These early star clusters only have about 0.01% of the masses and numbers of stars found in the Milky Way, meaning that for the first few 100 million years of our universe, the stars within it are barely enough to make a difference in the neutral matter permeating all of space. But that begins to change when star clusters merge together, forming the first galaxies. As large clumps of gas, stars, and other matter merge together, they trigger a tremendous burst of star formation, lighting up the universe as never before. But note that the process of reionization is uneven and doesn't complete at the same rate in all locations and directions. On average, it takes 550 million years from the inception of the Big Bang for the universe to become reionized and transparent to starlight. We see this from observing ultra-distant quasars and ultra-distant galaxies. But because there are a few directions where the matter is reionized much earlier than average, it indicates to us that structure formation is uneven and gives us hope of finding early galaxies even before that 550 million year limit. Hubble uncovered one such galaxy, GN Z11, whose light comes from an earlier time than the completion of reionization, just 407 million years after the Big Bang. However, other more distant galaxies have since been discovered by James Webb that are invisible to Hubble's capabilities. As Webb's sensitivity to longer wavelength infrared light allows it to see features that are more difficult for neutral atoms to absorb, the universe becomes effectively transparent earlier at longer wavelengths when less reionization has occurred. Infrared eyes are what it takes to probe the epoch of reionization itself. At the most extreme cosmic distances ever probed, there are not yet galaxy clusters in the universe, and the first galaxies, which are largely thought to have taken shape between 200 and 250 million years after the Big Bang, cannot be revealed by visible light observations alone. But through the eyes of an infrared observatory, where the light is long enough in wavelength to not be absorbed by these neutral atoms, this starlight might shine through after all. So it's no coincidence that James Webb was designed to look in the near and mid-infrared portion of the spectrum, all the way out to wavelengths of 30 microns, some 50 times as long as the longest wavelength light that human eyes can see. In fact, of the top 10 galaxies known at the end of 2023, 9 of the top 10 spots are James Webb galaxies, with GN-Z11 the sole confirmed galaxy not requiring either discovery or confirmation with the Webb telescope. The light created in the earliest era of stars and galaxies plays a cosmic role whose importance cannot be overstated, the role of making the universe transparent to all wavelengths of starlight. The ultraviolet light works to ionize the matter around it, enabling visible light to travel progressively farther and farther as the ionization fraction increases. The visible light gets scattered in all directions until reionization has gotten far enough to enable our best telescopes today to see it. But the infrared light also created by the stars passes through even the neutral matter, giving our 2020s array telescopes a chance to find them even where no visible light is available. Once starlight breaks through the sea of neutral atoms, even before reionization completes, it gives us a chance to detect the earliest objects we'll ever have seen. It's no surprise that even in just its first 21 months of science operations to date, the James Webb has broken a slew of cosmic records, including records for the most distant galaxy, most distant protocluster of galaxies, most distant black hole, most distant red supergiant star, most distant gravitational lens, and most distant quasar. The most distant reaches of the universe are slowly succumbing to our improved observatories, bringing the previously unseen into view. And according to the latest observations, astronomers have used the Webb telescope and an effect predicted by Albert Einstein over 100 years ago to discover that small galaxies in the early cosmos packed a massive punch, shaping the entire universe when it was less than 1 billion years old. The revelations from this discovery are profound. Combined with the power of gravitational lensing, the Space Telescope was able to see some of the earliest galaxies. Among them were Lyman continuum-emitting dwarf galaxies, some of the faintest objects in the early universe. These findings are in a new research article led by Hakim Atek, an astronomer at the Institut d'Astrophysique de Paris, published in Nature titled "Most of the photons that reionized the universe came from dwarf galaxies." Atek and his fellow researchers found 8 ultra-faint dwarf galaxies in the early universe. Contrary to previous thinking, these 8 galaxies were prodigious emitters of ionizing Lyman continuum radiation. Despite their apparent faintness, they emitted 4 times more ionizing radiation than previously thought. This helps cement their status as the objects responsible for the epoch of reionization. As team member Irina Karinskaya of the Institut d'Astrophysique de Paris in France said, "Without gravitational lensing, we would not have seen these very faint galaxies. This gives us a first look at the most abundant sources of ionizing radiation in the universe, the smallest galaxies." This article explains how these dwarf galaxies allowed the formation of massive stars, as they would have been some of the earliest objects to form in the universe. This release of ionizing radiation started the epoch of reionization. This era of reionization that started about 1 billion years ago remains one of the most important timeframes of our cosmic history and one of the most challenging to study. Before this, the universe was filled with a haze of neutral gas that kept light from passing freely through it. As these dwarf galaxies came to life and formed their massive stars, their radiation pierced the neutral fog, allowing light to travel freely through the cosmos and enabling us to view the universe as it is today. Webb, with its extreme sensitivity and high resolution, continues to change our understanding of how the early universe evolved. The massive punch packed by small, faint galaxies played a significant role in making the universe as we see it today.